I'm Louise Steinman, the program director for the Library Foundation of Los Angeles, which makes all of these free allowed programs possible. Edward Frenkel has set himself a challenge. He wants to, quote, unlock the power and beauty of mathematics for the general publics, and that includes mathophobic me, there might be some of you out there too, who was traumatized when my older brother tried to teach me square roots at the age of 2. I've actually never gotten over it. And I've confessed to Edward, and he has hopes of healing, if not entirely converting me, but I may be on my way. And Edward Frenkel is a man who likes challenges. In fact, I think he thrives on them. He was born in the Soviet Union to a Russian mother and Jewish father at a time of openly anti-Semitic policies at Russian universities. Moscow University essentially blocked him from pursuing his dream of attending that school, but he was not daunted. He snuck into lectures and seminars. He read math books on his own, and in the end, he writes, I was able to hack the system. They didn't let me in through the front door. I flew in through a window. When you are in love, who can stop you? Indeed, one reviewer called Frenkel's book, Love and Math, a sweeping romantic love story in the classic Russian tradition. When 20-year-old Edward Frenkel's student papers were smuggled to the West, they found their way to Harvard, where he was soon invited to come over as a visiting professor. And in that time, since then, he's become one of the 21st century's leading mathematicians, a professor at UC Berkeley, where he works on one of the biggest ideas to come out of mathematics in the last 50 years, the Langlands Program. Edward Frenkel's passion for math inspired him to co-create a short art movie. He said he was in Paris and was inspired by the directors there. And though I have not researched this, he is probably the first mathematician to appear nude on film, as he does in the silent Rites of Love and Math, in which he tattoos, quote, a formula of love on the naked body of his lover. One reviewer wrote of Frenkel's book, with every page, I found my mind's eye conjuring up a fictional image of the book's author writing by candlelight in the depths of the Siberian winter, like Omar Sharif's Dr. Zhivago in the David Lean movie adaptation. Love and Math is Edward Frenkel's Lara poems. This passion for mathematics shines through Frenkel's book, and it can be contagious. I did find myself this past weekend explaining to a friend why the round table at which we were sitting was symmetrical as opposed to the square table on the patio. Now that was new. Frenkel writes that math, quote, directs the flow of the universe. Math, he believes, is as elegant as music and as much a part of our intellectual heritage as literature. Tonight, after he gives a brief presentation, he'll be joined by screenwriter and the XFiles creator, Chris Carter, who has been described by Time magazine as a televisionary. Chris Carter created one of the most successful television franchises of all time, as we all know, with his award-winning show, The XFiles. He also created the shows Millennium, Harsh Realm, and The Lone Gunmen, and he is currently helming Amazon Studios' very first TV drama pilot, The After, which he wrote and directed, in which a friend who just saw it said, the first 30 minutes were great, the next 10 minutes were intense, and the last 10 were phenomenal. So please welcome Edward Frenkel and Chris Carter to the LA Public Library.
Hello, how are you guys doing? Welcome, thank you for coming. It's such a great pleasure to be here at Los Angeles Public Library. Thank you, Louise, for the invitation. Thank you, Chris Carter, for sharing the stage with me here tonight. And thank you all for coming. It really means a lot to me. Really excited. A library, I mean, isn't it wonderful that they still exist? And I think we should all support our local libraries. Well, I live in Berkeley, California. Well, kind of my local library too, if you think about it. So tonight I want to talk to you about love. Of course, Valentine's Day is coming up, so that's appropriate. And so I want to show a few slides, just give a short presentation. I want to talk a little bit about how I see mathematics and how I see the connection between love and mathematics. Can you all hear me all right, by the way? Yeah? You know this old joke about which mathematician is an introvert and which one is an extrovert? The one who looks at his own shoes as he's talking to you is an introvert. And the one who looks at your shoes is the extrovert. I suppose by that definition I'm an extrovert. But if my voice trails off, please tell me, I'll speak up. So I think we have a problem, and I don't mean just in this country, I think in the world. And the problem is that mathematics, which is a critical and crucial and essential subject, is so misunderstood. And I want to talk to you about this. One of the sort of metaphors I use in my book, Love and Math, is I compare the way mathematics is taught in our school to teaching an art class in which you only talk to the students about painting fences and walls. You only teach them painting a fence over and over and over again, but never show them the paintings of the great masters like Van Gogh and Picasso and Michelangelo. So then, naturally, years later, people will say, oh, I hate art. I was so bad at it. It wasn't just my thing. Why did we even have to study it? If I need to paint my fence, I can always hire somebody to do it for me. And of course, that conversation just misses the main point. And the main point is mathematics is so much more than painting a fence. It's much bigger and much more fascinating than most of us are led to believe. It's an amazing parallel universe full of beauty and elegance, which is intricately intertwined with ours. But if I had to summarize sort of in one sentence why we need mathematics, I would say it's because we live in this brave new world in which the king is not weapons, it's not guns, it's abstraction. Our world is built on abstraction more and more. And mathematics is the language of abstraction. And that's why it is so essential. And that's why we have to teach our kids mathematics, because that's what will make them fluent in the language of abstraction, and we will prepare them for the challenges of this new era. What am I talking about? Think about it this way. In old days, all trade was done through barter. You would exchange various goods or services. Then, of course, came gold. Then came money. But nowadays, sort of a fistful of greenbacks is really replaced by this little plastic card. I don't carry so much cash with me anymore. I carry a credit card, which I swipe, and buy things. It's not even that. It's more like a record on a computer screen or a line of code in a Bitcoin ledger. Very soon it's the last one, which will be the last remnant of money, so to speak. And we will be telling our grandchildren, used to be that we carried wallets and cash and credit cards. So mathematics is not about numbers and calculations. It's about concepts and ideas. And these ideas are the wonders of the modern world. And I don't want to talk for too much because I'd like to have a conversation with Chris, and I think there's a lot of interesting things I want to ask him, and perhaps he wants to ask me. But I want to give you a couple of examples, because now that I told you that there is so much more to mathematics than you were led to believe, then the natural question is, what is it? Tell us. Well, now that I got your attention, let me tell you a couple of things, just a couple of things. One, I want to talk to you about this beautiful idea of Riemann surfaces. Riemann was a German mathematician who lived in the 19th century. And he had this idea of describing curved shapes. He created the most beautiful, most satisfying theory of curved shapes, which we still use today. And this is an example of a Riemann surface. It's just a sphere. The surface of the Earth, for example, is a sphere. I'm not talking about the interior. I'm just talking about the surface itself. Okay? Here's another example, the surface of a donut. I bet you Homer Simpson would love that one, right? We call it a torus. That's another example of a Riemann surface. Here's a double torus, the surface of sort of a Danish pastry, if you will. And if you imagine a pretzel, that's another Riemann surface which has 3 holes, and so on and so forth. So you see that's the beginning of this beautiful world. And one thing I want to explain is that, see the contrast between those surfaces like a sphere and donut and so on, and just a plane. For example, this floor, or imagine a chessboard which extends infinitely far in all directions. It's tiled with squares, and each square has, the sum of angles is 360 because 90, 90, 90, 90. So that's one picture. And look how different the sphere is. The sphere is also tiled by this sort of like crooked squares. But if you measure the sum of the angles, they will not sum up to 360. They will sum up to a larger number. So that's what I mean by a difference between Euclidean geometry, which is, by the way, the only way most of us ever get to see anything geometric is through Euclidean geometry, through the lens of Euclidean geometry, which, by the way, Euclid wrote around 300 BC. So, 2,300 years ago. And by the way, most of our curriculum is like that. Everything is more than 1,000 years. Imagine that in a biology class or in a physics class, you would have a curriculum which is 1,000 years old. How would you know about solar system, about atoms and DNA? But why is it that in mathematics, we have a curriculum which has not changed in 1,000 years or more, and no one is complaining? Well, I am complaining. And so this is one of the elements. Why can't we show our kids the human surface, a sphere, and explain to them the difference between a flat space and a curved space, between Euclidean and non-Euclidean? Why is it important? It's important because actually the space which we inhabit, the three-dimensional space, which we normally think of a Cartesian, Euclidean, flat three-dimensional space with three coordinates perpendicular to each other, actually is not flat. Our world is actually a lot more like this. And you don't need to take a red pill, as Neo did in the Matrix, to see that. All you need is to learn some mathematics. This is a picture of a three-dimensional sphere, which is sort of one dimension higher than the two-dimensional sphere which I showed you earlier. It's very hard to imagine it. So here, an artist, actually my colleague from University of Toronto, Dror Barnatan, has shown it using something called Hopf vibration, creation of a German-Swiss mathematician, Hopf, in the 1930s. So it's a beautiful picture and beautiful example of a geometric shape, which is three-dimensional, just like our world, but it's not flat. It's curved, it's non-Euclidean. And guess what? Our world may well be more like this than the most boring and, kind of habitual Euclidean three-dimensional space. How do we know? Because of Einstein. Einstein showed that our space is curved. Gravity, the force of gravity, curves space-time. And our space is curved, so if you observe a ray of light, it curves around a massive object, around a star. And this, by the way, is a headline from the New York Times, 1919, when Eddington's expedition confirmed Einstein's theoretical prediction. But how did Einstein make this prediction? His work was based on the work of Riemann. Einstein's work was based on the work of Riemann, which was done 60 years earlier. So Riemann knew something. And he wasn't doing this because he wanted to describe the world. He was working within the narrative of mathematics. But this narrative is so powerful that he enabled Einstein and others who followed to make revolutionary discoveries about our world, the world that we inhabit, and to see that the things that we are used to are not what they seem, that our intuition, our imagination are limited unless they are supported by mathematical knowledge. Which brings me to this beautiful quote from Richard Feynman, that people who wish to analyze nature without using mathematics must settle for reduced understanding. So let's not settle for that reduced understanding. Let's learn more about it. Charles Darwin said he regretted later in his life that he did not learn enough of mathematics, but he said, I think that people who possess this knowledge are endowed with an extra sense. Mathematics gives us an extra sense, in the sense that it allows us to transcend our limited imagination. I wanted to talk to you about something in this regard. This is an article in the New York Times which came out last week by Dennis Overby, a New York Times reporter, about a subject which you may have heard about because it's been all the rage in recent weeks. The sum, 1 plus 2 plus 3 plus 4. How many of you have heard about this? Only a few. Okay, well. So that's actually a good example. Chris and I will talk about this. It's such an amazing, beautiful thing, which is completely, is a best kept secret. One of the best kept secrets in the world. We mathematicians, we keep it secret from the rest of the world. And the idea is that if you take 1 plus 2 plus 3 plus 4, and you start summing them up, and you get a larger and larger number. But actually, there is a context, there is a very rich context in which the sum, this actually can be assigned, this infinite sum can be assigned a meaningful value. And that value turns out to be minus 1 over 12. Who knew? The sum of all natural numbers, when looked at in a certain way, in a certain specific way, is actually minus 1 over 12. What does it all mean? The short answer, we don't know. We don't fully understand this. But more interesting question is, why are these beautiful and elegant mathematical results kept secret from everyone other than professional mathematicians? And so here, I would like to, I think we need help from Chris Carter, because I think that we should approach math a little bit as the X-Files. Because don't we all have this yearning for something mysterious and magic and wondrous? Don't we always try to find this experience which will transcend this sort of paradigm, the standard materialistic paradigm that we all learned? Don't we all think that there is something beyond the surface? Well, mathematics gives us examples of all of that. It allows us, to behold this magic beauty itself, uncluttered with misconceptions and dogmas. That's what mathematics is about. It's about finding those mysteries and wondering about them and looking at this magic, but not being satisfied and always stepping back and trying to understand and to give an explanation and to process information and to reach for even more difficult, even more sophisticated questions that will eventually help us to perhaps understand things which we couldn't even dream of. That's what mathematics is about. And finally, I want to say, and what's love got to do with it? I'm not going to sing, so don't worry. Although Louis said that I take risks, but okay, so this is even for me. I'm not going to do that, not tonight anyway. So, but what I want to say is that, of course, most of us, unfortunately, hate mathematics, quote unquote, hate mathematics. But again, as I said, what people hate is not mathematics, but painting the fence. The stuff that is fed to us, dressed as mathematics, which is not. But actually, there is more. So it's ironic that most people hate it, but actually, I think mathematics could give us additional rationale and additional meaning to our love for each other and for the world. And the reason is that mathematical ideas belong to all of us. We all know Pythagoras' theorem, for example. Pythagoras and Pythagoreans discovered it 2,500 years ago. And guess what? It meant the same thing to them, to Pythagoras 2,500 years ago and Pythagoreans, as it means to us today. To anyone in the world, no matter which religion, color, gender, cultural background, doesn't matter. We may not even speak the same language, but Pythagoras' theorem will mean the same thing to all of us. How many things are there in the world which have that quality, which transcend time and space, which are necessary, persistent, inevitable, and timeless truths? Mathematics gives us a huge reservoir, a huge source of such truths. And so, if they are like that, if mathematical knowledge is like that, it means that this is something that unites us all, that brings us all together, that this is something we all have in common, and no one can take it away from us. Even the courts have stipulated that mathematical ideas cannot be patented. No one can say, this formula is mine, E equals mc squared is mine, or some other formula. No, it belongs to everyone. And that's why I think mathematics is connected to love, could be sort of a foundation for love. A mathematical formula could carry a charge of love, just like a poem, or a painting, or a piece of music. And also, I think, it's also sort of a way for us to connect with our inner child. And Newton had these beautiful words to say. He said that to himself he appeared as, he's just like a little boy playing on the seashore and diverting himself now and then, finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. And I would like all of us to awaken to this hidden reality and to see what mathematics is really about. Thank you very much. And now I would like to welcome on stage Chris Carter, the creator of XFiles and many great films and television series. Which, by the way, do me a favor, go on Amazon and find the pilot of his new series, which is called The After. I watched it last time and I loved it.
Thank you.
Well, I mean, last night. It was amazing.
Thank you.
Yeah.
I just find it amazing that this man learned English by watching David Letterman.
It's true.
I'm also amazed that Newton looks so much like Michael Bolton.
I wonder if Michael Bolton is aware of that. Someone should tell him. So how do you want to do it? Do you want to ask me a question? Or?
Well, I created this TV show, and its kind of mantra was the truth is out there, and I just wanted to ask you, is the truth out there?
Is the truth out there?
Yes.
Oh boy. Some truths are out there. But I think what you're asking is maybe whether we could actually reach the ultimate truth and ultimate understanding of everything. And so there are several layers to this question, I think, which is, first of all, whether it's possible in principle, and second, what would happen if actually that could be achieved. And I personally think, there are all kinds of truths, but as a scientist, as a mathematician, naturally, I would first start with something like a mathematical truth or a truth about the physical world. For example, trying to find the fundamental structure of the universe, elementary particles, and how they interact, and try to describe all of this by a small set of equations. Something like Einstein's equations of general relativity describing the force of gravity, or the so-called standard model, equations of the standard model, which describes other known forces of nature. And the question could be asked whether actually we should expect that one day a physicist or a mathematician would be able to find the ultimate set of equations, and that basically those equations could be written on a T-shirt, so that everyone. Actually, I was at a school in Manhattan, Aspire Legacy School, just a couple of weeks ago, and one kid in sixth grade was wearing a T-shirt. On one side were the equations of the standard model, on the other side, equations of Einstein's theory of relativity. So it's not that far-fetched, but those equations are still incomplete. And there are different attitudes about that. So my personal view is that our quest for knowledge is endless. In other words, we will understand better and better certain things, but the more we understand, the more we will realize how little we understand. Mm-hmm. So we will push sort of the veil over the unknown, only to see the questions which we couldn't see before, and then we would want to try to answer those questions.
The reason I'm here talking to Edward is because I did a little fellowship, a writing fellowship at the Kavli Institute for Theoretical Physics in Santa Barbara. And Edward was there as well, and we met because of that. And we both met a man there who, when I met him, he just won the Nobel Prize, David Gross. And I was curious to find that this is a man who describes one of the most beautiful things I've ever seen, and yet he is an atheist. And it kind of shook me a little bit, and I never really got a chance to question him about it. But for me, I see science as a sort of a way to, I see it as a sort of quest for God and for meaning and for the ultimate truths. And I wondered if you, as a mathematician, a scientist, I think there are a lot of atheists as scientists, but as a mathematician, would you say that there are a similar amount of non-believers?
Well, the question, believers could be mean different things to different people, but I would say the following: that I certainly feel that there is spirit in the. So there is room for spiritual, just like I believe that there is room for magic in mathematics. And I got in some hot waters about this recently, because people were saying, it's not magic, it's not magical. But I said, yes, there is magic. And actually, if you look at the development of mathematics, there were mathematicians like Leonhard Euler or Riemann or others who actually took risk and who actually sort of jumped in the abyss of the unknown. And they were outlaws in some sense. They were doing stuff which was unlawful, was illegitimate. In only years later was justified and so on. Right. So that's an example of magic for me. Of course, you have to realize that the mindset of a mathematician, though, is that you would accept that as a magic sort of at first blush, but then you would always try to find an explanation, find a sort of put it in a sort of rigorous system of mathematics. But likewise, I also feel that there is place for spiritual, and it doesn't mean that one has to be religious or not. And actually, Einstein talked about that he said, he referred to Spinoza more specifically, and a philosopher who espoused very similar ideas, that if you sort of analyze the laws of nature, then you feel that there is a spirit, which Einstein said was vastly superior to that of a man. And as a scientist, you can't help but sort of feel the presence of that spirit. And as a mathematician, in some sense, I actually feel even more because, I said earlier that Pythagoras' theorem, for example, is something that was discovered by Pythagoras 2,500 years ago. But if Pythagoras had not lived, someone else would have discovered the same thing. So what does it mean? How is it possible that we discover these things, like mathematical entities, mathematical objects, and ideas, concepts, and theorems? Where do they live? I don't believe they're creations of the human mind.
Yeah.
So I think it poses a very big question. And so obviously, it informs, as a mathematician, as a scientist, realizing the power of these ideas and the spirit which they manifest. It certainly informs your quest for knowledge.
If in your book, there's something that, and even in my blurb, I mentioned this because it was fascinating to me, is that you say mathematics is an objective concept. It is. It's not just imaginary, it is apart from us, like the 12-tone music system that you can
right.
perceive this.
It's independent of...
It's in nature.
That's right. It's independent. It's not even... But you see, it's very interesting that I actually think that it also transcends nature. So there are two ideas that when one thinks about this, the two natural ideas. One is all of mathematics comes from nature. And of course, we can all count on our fingers and so on, and we see numbers everywhere. But there are concepts and ideas in mathematics which are not connected to physical reality in any obvious sense, at least not today. Maybe eventually they will be connected. And mathematicians discovered them without any reference to physical reality. For example, Riemann discovered Riemannian geometry without trying to describe the world. Of course, he knew, quote unquote, like everyone else, that our world is flat. He was thinking about those curved shapes as living in this enchanted gardens of Platonic world of pure ideas, I think. It just so happened that actually, it turned out later that actually those ideas had bearing on the physical reality. So I don't think that it quite cuts it, saying that all of mathematics comes from nature. Another idea is that all of these concepts and mathematical entities are creations of the human mind. And people would say sometimes, it's like chess game, it's like mathematical concepts are like pieces in a chess game, some elaborate fictions that we create. But I don't think that's true either, because no one has been able to use chess to make predictions about the world, but we use mathematics to make predictions which are tested all the time. The Nobel Prize was awarded last year, just a few months ago, to two physicists who theorized the Higgs boson. And their prediction was based on just doing some mathematics. So there is this big question, which I think is unanswered.
So are mathematicians simply discovering something that lives in nature?
That's what I believe. But it lives not necessarily in nature, but lives somewhere, I don't know where.
But it's not just imaginary, it's actually something that is discoverable.
It is discoverable because obviously we've been doing this for years. I mentioned Euclid wrote his elements 2,300 years ago, right?
Right, and you said someone else would have discovered them
exactly the same thing.
If he hadn't. But
so somehow we connect to this hidden reality.
It's interesting because you speak about math and music and art in the same breath. I just wonder if music is then, in your mind, similar a discovery. If Mozart wrote a beautiful sonata, would someone else have written it, also put those notes together in that particular way? Is that the same thing?
It's a very good question. And I would like to say yes, but I don't believe that's the case. I mean, there are certain very small segments which are, in some sense, inevitable. But one example I give is from a great writer, my compatriot, Mikhail Bulgakov. In his novel, The Master and Margarita, the master, who is a writer, burns his manuscript. But later he finds out from the devil tells him, manuscripts don't burn, don't worry, it's out there. And he gives it back to him. And this is such a wonderful sentiment, that, or like you said, Mozart did not live, somebody would write. But I don't believe it's true. I mean, writers have burned manuscripts and they never came back. Another compatriot of mine, Gogol, burned the second volume of Dead Souls, and we don't have it. We don't have that novel, unfortunately. So, what does it mean? But if Pythagoras Pythagoras wrote, x squared plus y squared equals z squared, and then he got so depressed that he decided to burn it. no problem. Someone else would have discovered exactly the same thing, you see. So my opinion, I might be biased because I'm a mathematician, obviously, but I think that there is something very special. But music, you're right, music comes as close as possible, so close second in that regard. I'm not saying music, second, whatever. Of course, music is equally important. But it's a very interesting distinction that we can make, I think.
I like to think that someone else would have created Gilligan's Island other than Sherwood Schwartz.
What about X-Files?
It's true, someone else would have created the X-Files.
I don't know. I don't know about that. But speaking of X-Files, I read somewhere something you said in an interview. And you said that the two characters of the X-Files came right out of my head, you said. And it was a dichotomy. They are the equal parts of my desire to believe in something and my inability to believe in something. My skepticism and my faith. I want, you said, like a lot of people do, to witness an unusual phenomenon, and at the same time, I want not to accept it, but to question it. And so these two characters and their voices came from that duality. And I was really struck by this. And I was wondering if you could tell us a little more, because maybe to be more specific, do you think that this dichotomy is something that we are born with? In other words, this longing and yearning for mystery and wonder and magic, but at the same time, the skepticism, not willing to accept it, but willing to argue with it and trying to find out more? Or is it something that we learn?
You and I discussed this briefly. I'd like to say it's innate that we have, as thinking people with a consciousness, whatever that is, we have that built-in desire to understand existence and consciousness and creation, and to it's man's search for meaning, I think, and I think that's universal.
Well, I mean, the search for meaning is universal, but you're saying something more than that. You're saying that there's also the yin and yang of that process, that it's a dialectic process where the sort of two opposites are kind of struggling with each other.
Yep.
So in a sense, then, I guess one could interpret the series as sort of something that's happening in the mind of a
it's faith and science. It's faith in something that is mysterious and
kind of more
unknowable,
right.
and science, which is rooted in what is provable and what is concrete.
But do you think that in science itself, as a process of discovery, there is room also for that mystery, for that sort of maybe not necessarily sort of moving, but not being assured of the truth, but kind of trying out different things?
Yeah, and you were saying that scientists live, and mathematicians live in a state of uncertainty and chaos and frustration, and I think that is built into the idea that you're speaking of. It is a frustration with what we know to be true and what we want to be true.
So the frustration is because of that struggle between those two sort of opposite desires.
Yep.
Yeah, you're right, and it's sort of interesting because I got some of the people commented on my book, and they said, I couldn't understand this thing, or I couldn't understand that thing, and I said, welcome to my world. This is what we do. 90% of the time, when a mathematician works on a problem, he or she is frustrated, unhappy, unsettled, thinking, oh my gosh, I'm so stupid, I can't understand it, things like that. That is part of the course. But not only that, I think that's what, in some sense, is driving this. And I like what you're saying, that what is the source of the frustration? The source of the frustration is precisely in trying to combine two incompatible things. That on the one hand, you are seeing something which you want to understand, but why do you want to understand it? Because you see that it's something mysterious, right? I mean, that's why you want to understand. But then you can't understand it, right? And that's a very interesting point. I didn't think about it in exactly in exactly the same way. But then, I'm just curious, is that what, I know that you're very interested in science, and you and I connected because through the Kavli Institute for Theoretical Physics at UC Santa Barbara, and David Gross, who is our mutual friend, and so is Sarah Vaughan, who works there. But I'm just wondering, is that what brings you to science? Is that what you find so interesting about science?
I don't know how to answer the question. I have a brother who's a scientist.
Okay.
He introduced me to science, even though he's 5 years younger, he introduced me to science fiction, which I think was my entree into science. It's, I think, something that we share, but our approach to science, mine was through television, writing, and his was actually, he's a material science professor. You know, it's something that I think we were raised with.
Okay. Well, it's interesting because my sister is a musician, and so in that sense, I admire music, but I know that I'm not. I can't be well, I shouldn't say I can't be, but it's not something that I feel that I'm confident doing. So it's kind of interesting how sometimes different areas are kind of distributed between siblings.
I have a question for you. You've written this book, and it's a popular book. It's a bestseller. It's gotten terrific reviews. And one of the reasons that you and I are speaking is because I had the pleasure of introducing Brian Greene to an audience at Santa Barbara. And when I was telling that to a friend who is a scientist, he looked at me and smirked, and he said, Brian Greene he's a popularizer. He's a person who is, you know, reducing something complex and arcane to a palatable subject for a mass audience, and he was snide about it. You're a popularizer. Have you?
And I'm proud of it.
Yes.
Yes. And more mathematicians and scientists should do that.
I'm just curious, though.
Right.
I work in a business where I would. There are a lot of haters. And it's not hard to find them. Anyway, I just wondered, has this engendered is there a backlash? Is there a part of the mathematics community who thinks that you've actually done them a disservice?
Very good question. Probably, but no one told me so to my face. And actually, my colleagues at Berkeley have been very supportive in particular. But it's very interesting what you said. So first of all, about Brian Greene, I think Brian Greene basically single-handedly created a revolution in science writing with his book Elegant Universe and other books that followed, World Science Festival and so on. I mean, Elegant Universe really, to me, is like the gold standard of popular writing about science. And actually, he was not reducing things. On the contrary, I think when I read his books, I actually learn something, even if I know the equations and that sort of the details, technical details. The way he presents the material actually illuminates it even for experts. So to me, this comment is very telling because you're right that there is, but it's not just in science. I think it's sort of true in everywhere that people who go out and try to tell the world about what's happening in a particular discipline are kind of looked upon in a certain way. But it's especially true in mathematics in the following sense, that we have created this elite. I mean, let's face it, mathematicians is sort of a modern day elite. We are, it's like a cabal. We have this sect of people who know all the secrets. Why is it that no one knows about 1 + 2 + 3 + 4 being, when you look at it in a certain way, in a certain very interesting way, is -1/12? Why did it take a filmmaker from Britain, Brady Haran, who is not a mathematician, to tell the world about this? Why is it that mathematicians, professional mathematicians like myself, don't talk about this stuff? And that's a very serious problem, I think, because how can we expect, I was talking earlier about this, that most people, in the eyes of most people, mathematics is like painting a fence. But then how do you expect people to know what is out there? What are the great paintings? What are the masterpieces of great mathematics? If we mathematicians, people who know this stuff, who live and eat and drink this stuff, if we don't go out and tell people about it. So we must do it, and even if someone is not happy about it, they'll have to live with it.
In reading about math, my brother introduced me to the book A Mathematician's Apology,
Oh, yes.
which is an really interesting little book. And it's
G.H. Hardy, a great
G.H. Hardy,
British
yes.
mathematician,
Yep.
wrote it in the mid-20th century.
He brought up something which I think is interesting, and he said that mathematics is a young man's pursuit, and that Newton burned out at 40 and didn't do any math after 50. Is that true today?
Well, I'm only 25, so I don't know. I guess I'll find out. But it's a very good point. So there is this myth somehow that mathematicians burn out early. And I think when Hardy was writing this, he was sort of feeling that his mathematical abilities were declining, which I don't think was really true. I mean, in some ways, as you become more mature, maybe you're not as quick in terms of doing calculations and so on, but I think you start choosing the subjects of your investigations more wisely, and you sort of distribute the effort in a better way. But there are a couple of fascinating examples of mathematicians who discovered some amazing things very young. Évariste Galois, a French mathematician who lived at the beginning of the 19th century, was killed in a duel when he was barely 20 years old. I talk about him in my book. And he discovered this theory, which we now call after him, Galois theory. There are a couple of other examples like that. But actually, these days, that's not really true, because in part for good and bad reasons. I mean, good reason is, I guess, people now do amazing stuff at much older, more mature ages, I suppose, than before in general. But also, sort of a negative element is that mathematics has become so fractured and specialized that for a modern-day graduate student, it takes years and years to actually learn the stuff to the point where they can actually do their own independent research. So oftentimes they come up with their first papers when in their late 20s. So that's surely not the same situation as Galois was in the 19th century. But so yeah, I think it's there is place for mathematics for people of any age. That's what I would say to this.
What else was I thinking about?
By the way, going back to the G.H. Hardy, there is something very interesting about this book, that his main thesis is that one of the main ideas that he puts forward in that book is that mathematicians are not driven by applications, that we are driven by finding beauty. And so it's very interesting, and he was actually, so in a way, it's an interesting question whether he was right or not, and ironically, he was talking about his research being useless, his research in number theory. Yeah. And of course, he was basically, his point was, he was basically saying, oh, people always complain about how mathematics is useless, and they always ask, what is it good for, and so on. And he sort of was defiant, and he said, well, guess what? It is useless. Leave us alone. We are not there to work on applications. We are actually searching for the higher beauty. And he was right. But ironically, his work, the kind of work that he did, is now ubiquitous in the digital world, because we use number theory, some really sophisticated mathematics, coming from number theory, in encryption, for example. Every time you punch your credit card number on a computer, it gets encrypted when it's transmitted to an online vendor, or your account number, on a bank account number, and things like that. And I would say even more, that actually, that brings me to another topic, which is also the power of mathematics in today's world. And we recently learned, for example, that this power could be abused, for example, through the revelations about the NSA surveillance scandal. We found out that NSA was tampering with some of these encryption protocols, and they were inserting some backdoors into these protocols, and they were exploiting very sophisticated mathematics. And so the question, in a sense, it's sort of like the joke was on Hardy, because Hardy was saying, well, it's useless and so on, but actually it is useful, as it turns out. But it's actually more than that. It's not just it's useful, it's actually very powerful. And I wrote, about a year ago, I wrote this article in Slate, where I talked about something else, about manipulation of economic statistics, where again, sophisticated mathematics is used to change the way inflation is calculated, which has tremendous implications for all of us, because our tax rates change, taxes go higher, and social benefits go lower if this measure of inflation is the way we calculate is changed. But nobody complains because people are afraid to talk about mathematics. And I said, look, we always talk about the Second Amendment, the right to bear arms. But in the 21st century, the real weapon is mathematics. So the Second Amendment for the 21st century should say the right to bear mathematical arms. You look startled.
You heard it here first.
What I mean by that is giving our kids, our students, the necessary tools to thrive in this new world, which is based on mathematics.
There's a guy named John Brockman who asks a question, and he's actually published the book full of the answers, which is, what do I believe but cannot prove? And he asks a lot of smart people, scientists and philosophers and thinkers, what do they believe but cannot prove? And I'll ask you the edge question.
You go first.
No, it's after I asked you.
I believe that I will answer first. What cannot prove. That's an example of a kind of a thing a mathematician would say. The extrovert. So anyway, what do I believe? But I already said that. I think that mathematical ideas exist outside of space and time. I mean, it's kind of a silly expression because the word outside already assumes that it's within space-time. But they are timeless and transcend physical reality, and that's what I believe. And I believe that humans, in some ways, are capable of connecting to these ideas. I cannot prove this, but this is what I believe. And my experience, my work in mathematics, convinces me of this. And so for me, it's kind of like sometimes people who believe this are called Platonists, because Plato was the philosopher who theorized that there was this Platonic, what we now call Platonic world of ideas, and that's where mathematical ideas presumably should live. And in Plato's eyes, it would be sort of a perfect world, which would be a counterpart to the imperfect and messy, real world which we perceive, which we inhabit. But I actually think mathematical world could also be very messy, so it doesn't have to be necessarily so tidy and clean. It would actually make it more interesting. But I do believe that there is this mathematical world of ideas which is independent from physical reality and consciousness, but I cannot prove it.
Perfect segue. I was reading about Plato, and he said that good literature clouds our thinking, and he suggested that we put a child to bed with a book, Euclid's Book of Geometry.
That would put the child to bed, just like that.
Well, how do we do that, though? I mean, if math education is something that is lacking and we need to figure out another way to teach children mathematics so that they see the beauty of it, as you are suggesting, how are we going to do that?
I'm glad you asked me this. So I have an idea how to do it. And it will sound a little crazy, but here's what I think. I think our discussion about this question of how do we teach kids mathematics it would be like discussing how do we teach art to children, when actually we would be talking about whether or not we should teach them painting the fences and walls, and how we should teach them painting fences and walls. Should we teach them painting the walls, or should we not teach them painting the walls? Does it matter or does it not matter? But what this kind of discussion would miss is the fact that art is not about painting the walls. And our discussion of math education today is lacking because we are discussing a very tiny part of mathematics which was created more than 1,000 years ago. So what we should be instead discussing is what is real mathematics. Now, I went 2 weeks ago, I already mentioned that. I went to a school in New York, Spire Legacy School. I went to 4th, 5th, and 6th grades, which, by the way, I was terrified. Because these kids are so smart, their minds are still uncluttered with all this stuff that we learn as we grow up. Nobody told them yet that math is impenetrable. Nobody told them yet that they won't get it. Nobody told them yet what they can or cannot do, what they can or cannot be. And they are so ready for this. I explained to them Riemann surfaces. I explained to them symmetry groups, the kind of stuff I talk about in my book. And they got it just like this. And the stuff they didn't get because they didn't have enough time, I know they can go on their iPads and computers and Google it and learn it faster than I could ever explain it to them. So the kids are ready. It's the adults that need to learn this stuff, because it's the adults who decide what should be in the math curriculum. So my suggestion is that all of us should learn something about this magical, what it is. It really is a magical world of mathematics. Go to a library, get a book about mathematics. Not necessarily my book, could be. There are plenty of other books. Go on YouTube and watch some videos about mathematics. Watch a movie about mathematics. Learn something. And try to get a big picture of mathematics the way all of us have a big picture of art and literature and other sciences. And when we do that, we will do away with the question, why do we need mathematics? Should we learn mathematics or should we not learn mathematics? We will be then in a position to help our children to acquire the necessary knowledge to thrive in the 21st century.
We began our conversation talking about David Gross at UCSB. And he said to me, when he won the Nobel Prize, he got a chance to travel the world. And he was alarmed at how far ahead the Chinese are in science education, and how far ahead India is in science education compared to America. And he said, we desperately need another Sputnik, this Russian satellite that went up and created a space race and an interest in science and a determination to teach science and to children in America. A lot of money and energy was thrown behind that. Do you believe that as well? And are you Sputnik?
Beep, beep, beep. Well, Sputnik, I mean, so this was really because of the military applications of this stuff, right? So it was because the relations between the Soviet Union and the United States were adversarial, which was a bad thing, of course, but as always, there's some bad things could have some positive implications, and this was one of them, that this led to some effort, additional effort in terms of science education and so on in this country. But I don't think we need to find another enemy to do that. How about love? How about just realizing that mathematics is a basis for love? Because it's the stuff which unites us all. We don't need to find an enemy to motivate ourselves to learn about the space we live in, to understand what does it mean that one space is flat and another one is curved. What does it mean that a ray of light curves around the sun? Why do we need an adversary for that? We don't, right? So that would be my answer.
I see.
Does it make sense?
Yes. I think we're about to our question and period here, and so I think we're going to throw the conversation out to the audience and.
I got to be the first question. You described the difference between, or you talked about the difference between the math that we are teaching our children and real mathematics, but you didn't say what real mathematics is. Can you explain a bit what you mean by that?
As Stephen Colbert says, in 5 words or less, right? So, well, I try to explain in 10 minutes or less, a little bit, right? So, there are several. Here's what I think. I mean, in my book, I describe how I came to mathematics. I actually hated mathematics when I was at school, just the same way as everyone else, because I thought that all mathematics revolved around the stuff that they were teaching us. You know, some arithmetic, some quadratic equations, some trigonometry, Euclidean geometry, and so on. I was sure there was nothing else. But I was very interested in physics, in elementary particles and interactions between them. And that was my portal, you see. So there was someone in my life when I was 15 years old, who explained to me, was a professional mathematician, explained to me that the only way to understand this stuff is through mathematics. And I was, as I say, you know, I was instantly converted. So I became a convert into mathematics. Like, oh, he showed me a book and he said, that's the explanation. And I had no idea. So those were the glimpses of this magical universe I was talking about, this magical world. So for me, it was through the world of physics. For someone else, it could be through biology, or it could be through art, or through music, you see. So each of us will have our own. There are many different portals. There are many different doors. Right now, they're all closed. But you have to find just one. And once you find it, you go inside. And then one thing will lead to another. You will want to know more. So what I threw out there at the beginning were just like two portals. One was, Riemannian geometry, this idea of curved shapes and how it informs our understanding of the physical reality through the work of Einstein and others. And the second one was this idea, this outrageous idea, that if you sum up 1 plus 2 plus 3 plus 4, then actually in some very specific, rigorous mathematical context, you're not going to get infinity, but you'll get minus 1 over 12. How can it be? So these are two examples, but there are so many more, you see. So I hope I convinced you. Great.
In business, the big buzzword is big data, which is like painting the fence as you described it. It's very sterile and there's no soul to it or anything. What can you say about the more elegant part of mathematics and business? And to follow up to that, would you write some articles about that for the popular press to spread the word about it?
Very good question. So I mentioned already earlier this idea of measuring inflation, for example. And so this is something which has perplexed economists for many years. How do we measure inflation? So there are certain formulas, but they have deficiencies. And this is the stuff which is, it's our bread and butter, so to speak, because depending on what our government economists say, the CPI, Consumer Price Index, which is a measure of inflation, is every quarter. Depending on that, our social benefits are adjusted, our tax brackets are adjusted. So tens of millions of Americans are affected by this. But it's all based on a particular formula. And it so happened, for example, that in 1996, the government changed the formula. And the idea was that you would lower that CPI, so you replace with you put another formula in. The answer will be slightly different, but that slightly would save the government $10 trillion. And I wrote an article in Slate about it a year ago. You can easily find it. So this is one example where there are two aspects here. Number one is, why didn't, people weren't, if the government said we're going to lower your benefits, increase your taxes, everybody would be up in arms. But they said, there is this very obscure and arcane mathematical formula. You don't want to know about it. We're going to change it because some very important economists say that it is wrong. So we'll replace it with another formula, and then whatever comes out, comes out. But actually, they knew the answer, so they changed as it turns out, they knew what answer they wanted to get. So there wasn't enough discussion, and I think that is a problem because that's exactly why I talk about, the right to bear mathematical arms. I dream of a society in which our citizens would not be just standing by when such a crucial formula is replaced by another formula, but they will ask the question, why? Why are you doing this? I want to find out more. Maybe not all of us can understand, but maybe my neighbor understands. I don't understand, but my neighbor will understand and will explain it to me. This kind of stuff. So that's one aspect. But the second aspect is, what is the right way to measure inflation? The question is still open. And there's some very interesting results, which I've read, by economists Weinstein and Malani, who say that actually you could use some very sophisticated mathematics, which is the same mathematics which is used in the standard model of elementary particle physics, which is called gauge theory. So that's fascinating. So that's an example of beautiful mathematics, which has already proven itself in describing the world, potentially having applications in economics.
What you're saying basically is never trust a mathematician.
Never trust an economist. That's exactly the point. That's the difference, because you see, in mathematics, we don't respect authority. We don't respect fashion. Pythagoras' theorem was Pythagoras' theorem before, and it's the same. It's not going to change next year, when the new season comes. It doesn't, and that's why we have this sort of very collegial, by the way, relations in our community. Like, we don't care, you can have graduate students talking on a first-name basis with professors, because we know that we are all in the same game. If you're right, you're right. What you say is either true or false in that realm of mathematics, you see. Other sciences are not like that, because economics is different, because then it depends a lot more on authority, on who is saying these things. And that's why mathematics is so important, because it's something we can all hold on to, because we can disagree on so many things. You can believe one thing, I believe something else. But 2 plus 2 is 4, if you calculate it correctly, right? And we can all agree on that.
Hi, gentlemen. Thank you so much for sharing your thoughts with us. So my question goes out to both of you. And you mentioned that are we built with this desire to wonder and search for meaning? And I think that kind of comes from when you're young and you kind of look up and you see this vast expanse of the universe and space ahead of you. And you said that perhaps if Pythagoras didn't come up with his theory, then maybe somebody else down the road would. So when you look at the universe, do you think that if there were others out there, it's a universal theory? Do you think that they're coming up with the same problems and the same solutions to what they view within the universe, or are they hearing different music and coming up with different ideas and seeing it differently?
Chris?
Well, I have a question. There's this idea, and it is this idea of a theory of everything, that everything can be reduced to a T-shirt. This seems to me to be sort of like a scientist's hubris, that everything could be understood.
Well, I would agree with you, but there are people who think otherwise. This is another example of something I believe but cannot prove, right? So I actually think it's not possible, as I already said earlier, but some people think it might be possible to understand something at the fundamental level. And then sort of there would be a very complicated hierarchy of theories which would be sort of applicable in other domains. So it's not that simple that you have just one equation which services everything. Which, by the way, was the subject of my film, which Louise mentioned at the beginning, a mathematician creating a formula of love. What does it mean? Could such a formula be created? But going back to the question about sort of if there were other minds in the universe, would they discover the same mathematics? It's very interesting. I would like to say yes, but it could be that, mathematical world is like a world, right? So I speak in my book about different continents of mathematics. And so, we didn't know, for example, Europeans did not know about America until a certain point, until Columbus or Vespucci or whatever, right? So you had to discover America. And so maybe there is some continent in the world of mathematics, which we humans living on Earth have not yet discovered. But another civilization, on the contrary, has discovered that continent, but not the kind of stuff which we take for granted. So it's possible that when we meet, we will sort of like exchange ideas. But I do believe that it's one world. So we might be seeing just parts of one part. Other civilization would see another part. But it is just one world.
A great conversation. There was this article on BBC either today or some days ago, which basically proved the point that you were trying to make, that on the mathematician's mind, the certain ideas which they consider to be beautiful, they evoke the same side of the brain, where for the other masterpieces evoke in other people's mind. The Euler's identity would be one great example of that. Now the question is that the Fermat's last theorem, in his original book, the way he wrote that the answer it was so simple, but he just didn't have the space to write it down. But the eventual answer that we have, it's so long and so complicated, it can no longer be considered beautiful. So I don't know, you may disagree with that, but the question is that how important the beauty of a proof is to you or to mathematical community in general. And also, is there possibly a smaller answer to the Fermat's last theorem too?
Very good question. So yes, first of all, there was this report on BBC, but they were referring to an article published by a neuroscientist recently. And actually, one of the co-authors is a prominent mathematician, Michael Atiyah, and they indeed talk about the fact that the same areas of the brain light up when mathematicians experience beauty, even if they cannot quite explain it to others who don't know. But presumably anyone who can, mathematics is in part, you can think of mathematics as a language, right? So, a formula like Euler's formula you alluded to is an expression on that language. So anyone can learn it, And then the point is that anyone presumably would have the same reaction to if one would experience it as beautiful. And of course, beauty is more subjective than truth. Truth is a mathematical formula is something which is independent of interpretation. It's either true or false. Well, before my colleagues would correct me, I sort of in parentheses, I would say it depends on the system of axioms in which you work, but that's a minor detail, so to speak. Okay, but But the notion of beauty is more subjective. However, likewise with music, you can have a particular piece, but many people would agree on Mozart music being beautiful. Likewise with Euler formula, most people would agree. And it's very interesting to me that the same areas of the brain light up when we experience that beauty for mathematical formula, right? So, but going back to Fermat's last theorem, so it's a very beautiful story that you were referring to. So Pierre Fermat was a French mathematician in the 17th century who made this discovery of an equation that he thought had no solutions, and he wrote it down on the margin of a book, and then he left a comment saying that he found a very nice proof, but the margin is too small to contain it, which I like to call as a 17th century version of a Twitter proof. So not enough characters, but if I only had 250 characters, I would explain. So, but the proof actually took 350 years. It was only completed in the 1990s by Andrew Wiles and Richard Taylor. And you're right, the proof itself takes many pages. And one could argue that it's not beautiful. But first of all, it's not clear whether it's true or not, because what actually they proved is not Fermat's last theorem, but they proved some statement which is part of the Langlands program, which I talk about in my book. But another mathematician, my colleague at Berkeley, Ken Ribet, connected that statement to Fermat's last theorem. So what they proved is some result about the Langlands program. The proof is long, and there are some tedious part in it, but the idea is actually very clear and beautiful. So, it's very interesting. Is it possible that we could reduce the tedium somehow, kind of surgically remove the tedium from the proof, and just leave the beauty? And it's a more philosophical question. Honestly, I think there will always be some tedium left. There will be some non-zero. There is a law of non-zero tedium, I think. And if you think about it, anything we do in life, you can't expect it to be just positive in some sense and rewarding. You have to work hard. To really get results, you have to work hard. So there will always be this element of, when you're not frustrated and not satisfied. And I think in mathematics too, that even the most, maybe if you could find the best possible proof, it would still have a certain element of some unsettling element in it.
3.5 brief questions. Very brief. Who is your most favorite mathematician that's active and current? What do you think of the work of Wolfram? I think the most beautiful number is 37. What's yours? And when was the last appearance on David Letterman?
Whose appearance? It hasn't happened yet. I learned English, as Chris pointed out, and I write about it in my book. I learned English by watching a David Letterman show. And I would like to go on his show and to thank him as my English as second language teacher. So I hope I will have that opportunity soon. But going back to your questions, the greatest mathematician who is alive, I think my favorite is Robert Langlands, because I think he's a man who laid the foundations for the Langlands program, which is the subject in which I work. My favorite number, I don't know, 1 - 1/12? What was the middle question? Did I answer all of them? Wolfram. Oh, Wolfram. I don't know enough about his work, but Mathematica, the software package he created is fantastic, and a lot of people use it. So have very positive views of that.
This is my chance to pitch the After. This is the television pilot I have on Amazon, where the numbers 3 and 7 do actually factor into the greater mystery.
That's right. That's right. And by the way, go on Amazon and vote for the pilot, because I honestly, if you watch the pilot, you will be dying to know what happens next. But we will not find out unless Amazon asks Chris to make more episodes. Do you guys want to see more episodes? Yeah.
My question is, do you think there's room for both danger and the political in mathematics? It was when you were talking about whether the two of you, the connection between writing and whether something had been written, whether someone else would have written it. I find that there's a lot of personality still in mathematicians, and there's maximalists and there's minimalists, and there's people trying to gather it all together, and there's people trying to get very little niche things, but there's still, beyond the dangers of what mathematics can create, the ability that it has as a language. I mean, even in misunderstanding, there's like the theory of relativity, and then people say that things are relative, which is obviously not what is meant. But so do you think that our inability to have a fuller understanding also is dangerous?
I think it's very dangerous, so I give one example is our not being able to understand the way economic statistics could be manipulated. Another one is, for example, I did a video recently in which I explained the mathematics that went into this backdoor that was inserted into a commonly used protocol for generating random numbers by the NSA. And it's sophisticated mathematics, but it can be explained. It can be explained. And I think it's very important that more people are aware of what this is. Maybe just getting a gist of the idea. So that we can have a serious conversation then about whether this is something that was a good thing or a bad thing. And also, I think it's important that our decision makers, people who actually, for example, decided to use particular mathematical models which led to the economic crisis, the global economic crisis, or people who were in charge of NSA making decision to employ particular mathematical methods. My question is that I think that it's very important that they are aware of the powers of mathematics that they unleash. Because let's face it, a mathematical formula could be just as powerful as a nuclear bomb. But we safeguard our nuclear technology. And so we should treasure mathematics, but we should also safeguard it.
I'm the keeper of the clock, so I'm looking at the clock and seeing that our time is up. For me, this is a big honor. I grew up in Los Angeles. That I'm sitting here on this stage at the public library is just an amazing thing that I'm talking to Edward. And that the series is 20 years old. I'd like to ask everyone, if you love the series, to please support the Library Foundation, and so that they can continue doing these wonderful events. Thank you.